So continuing from chemical properties due to the carbonyl group, first I'll tell you some very common ones followed by some very important from this chapter point of view. So reduction by hydrogen, very easy. So I write here carbonyl compounds will give rise to presence of hydrogen in PT or palladium or nickel, will give rise to alcohol. Aldehydes will give primary alcohols, ketones will give tertiary alcohols. That's very simple. Okay? Something. So now what about alpha beta? Unsaturated carbonyl compounds. Okay, let me take one example. So alpha beta unsaturated carbonyl compound. In case of alpha beta unsaturated carbonyl compounds, if the double bond is there, H2 by Na will reduce the double bond, but Li and H4 will not reduce. But if a compound contains acid chlorides and alcoholic esters, suppose acid chlorides and alcoholic esters, okay, that is esters are basically alcohols, are present in a compound, then your LiLH4, that is lithium aluminium hydride, will also reduce them to alcohols. This is the disadvantage of lithium aluminium hydride. But if you use NaBH4, that is sodium tetrahydroboron or NaBH4, this particular reagent affects only the carbonyl group and does not reduce any other group. Okay, LiLH4 will not reduce unsaturated one, but rate of reaction is fastest, better reducing it. So what I was mentioning, that NaBH4 is basically a selective reducing agent which reduces only the carbonyl part of a compound containing aldehyde and ketone, whereas LiLH4, its speed of reaction is very fast, but apart from the aldehyde and ketone part, it also reduces acid chlorides and ester parts and anhydrous also. So in order to have the specific alcohol that's required, if you use LiLH4, it should not contain any of these above groups, otherwise you will get a dialcohol different from the compound that you desire. Now we'll go to specific reduction reactions. First, using red phosphorus and HI. So you have aldehyde, this acetaldehyde. If you treat by red phosphorus and HI, you will get directly alkane, that is ethane. Okay, so red phosphorus HI gives rise to alkanes as the product. Then the next reaction is Clemmensen reduction. Clemmensen reduction, very important. So let me tell you a brief introduction to this. So ketones with phenolic and carboxylic groups is the substrate. Okay, so in Clemmensen's reduction, the substrate used is ketones with phenolic and carboxylic groups. Why? The reason is we'll be doing the reaction in the acidic medium, and phenol being an acid, carboxylic acid being an acid, they are not affected by the presence of acid. So phenolic and carboxylic groups, if they are present in a compound which is a ketone, then this reaction is favorable. But if any other compounds are there, the acid may end up in reacting, and if it's a basic compound, then a salt may give rise. So we generally avoid that. So please remember this particular point. So with what it fails? So it fails with acid sensitive compounds and high molecular weight compounds. Okay, so compounds having high molecular weight and acid sensitive compound fails. And an important point is alpha beta unsaturated ketones. So if you use alpha beta unsaturated ketones, it leads to the reduction of both the olefinic group and also the carbonyl part. So for alpha beta unsaturated ketones, both the olefinic group and the carbonyl group is also reduced. Okay, so that's the basic. So let's go for mechanism of Clemmensen's reduction. You have ketone RC double bond OR, and you conduct it in acidic medium. So basically we have studied nucleophilic and electrophilic addition, not to be difficult. So oxygen having the lone pair, H plus goes and adds here, so you get this. Now oxygen forms this, so you have a partial, in fact not partial, let's say positive charge on oxygen atom. So now its resonance structure is this. So both are in resonance with one another. Now this particular resonance form is important for this reaction. Basically a compound may have many resonance forms, but in a particular reaction, which resonance form that is present in that particular compound or the compound exhibiting that particular resonance form is effective in this reaction is to be known and is to be considered while applying the mechanism. So then you treat with Zn, which is having again the lone pair, so you get R, C, OH, R. So what happened? Zinc donates its pair of lone pair to this carbon atom and forms Zn2 plus because of the loss of 2 electrons. Okay, so now carbon has got 2 electrons. Before 1 electron shorted, 2 electrons added, so it gets a negative charge. Negative charge, acidic medium, picks up a hydrogen ion or H plus atom and forms R, CH, OH, R. Now, acidic medium picks up one more H plus, R, CH, R, oxygen having lone pair, donates it, so forms OH2. Now, so because of this, it gets a positive charge. What happens now? This pair of electrons shifts and this goes away as a water molecule. So, if you take minus water molecule, you get R, CH, R. This goes here, so water molecule goes out. So then this pair of electrons shifted, that means oxygen takes it and goes away. So you get a positive charge on this. Again the story continues. You have zinc over here, donates the pair of electrons, then you get CHR, the negative charge, and being in acidic medium, picks up a hydrogen ion and forms RCH2R. Now, acidic medium, no reaction. Zinc cannot donate because you cannot remove hydrogens from an alkane easily, right? Because there are no minus I group, no groups which are electron withdrawn, so removing hydrogen from alkanes is difficult. So the reaction stops at this stage because no zinc to add and no H plus to add to any of this and removal of any other groups from the compound. So you get the product as an alkane. So basically what happens? Protonation of the carbonyl compound. Once it gets protonated, then shift of charge, we take the resonance form, zinc donates pair of electron, carbon gets negatively charged, picks up a proton from the acid, and then again the compound gets protonated, removal of water molecule, positive charge, zinc donates a pair of electron, negative charge, and then protonation, you get the alkane. Remember, acid sensitive compound will not form there. Suppose if we have a base, so the base will basically react with the acid to form a salt without giving rise to any of this reaction. Because acid-base reactions are much more faster and stable than your carbonyl compound, because carbonyl compounds have a quite sufficient stability against any reaction. I tell sufficient, but in certain cases they tend to be more reactive to form a more stable compound. So that was about Clemmensen's reaction. In Clemmensen reduction, basically we use Zn in presence of any acid, and finally we get rise to an alkane. So let me write Clemmensen reduction. Suppose if you have this is Clemmensen's reduction. You have an aldehyde. If you have 4H added in the presence of ZnHg and HCl, you will get an alkane plus removal of water molecule, which you have seen in the mechanism. Right? So Clemmensen's reduction, the reagent is ZnHg, that is zinc is the active part and Hg is a zinc amalgam, and it's presented acidic medium, which is HCl. To prevent Zn to form ZnCl2, so Zn will form ZnCl2 if it's just present like that. So you have the amalgam, and in the amalgam part, Zn donates the pair of electron in the formation of the alkane. Some points: alpha hydroxy ketones. This may give either ketones or olefins, one of them being major, another being the minor product. Second, 1,3 diketones gives 1,3 diketone gives monoketones with rearrangement. Remember, 1,3 diketones give generally monoketones with rearrangement. Suppose this particular compound, this is 1. Okay, this is 1,3. diketone, you treat with ZnHg and HCl, you will get monoketone, which is formed by rearrangement okay. Now where the rearrangement takes, when the carbocation is formed, you know carbocations can always undergo rearrangement to form the more stable carbocation, and then because here you will form basically a secondary, it forms a tertiary, so this carbocation then H gets added, so you know the more stable carbocation is always preferred, right? However, if you have cyclic 1,3 diketones, it will give the fully reduced product, but another product will be formed, which is a ketone with a ring contraction taking place. Okay, so if you have this particular compound, CH3, CH3, and if you treat with ZnHg, HCl, sorry, I forgot the diketone part. So diketone, then you have the fully reduced form, that is this Me methyl group plus a rearranged product, which is a monoketone Me. So this Clemmensen reduction is very much useful for introducing straight chain alkyl groups without any rearrangement in aromatic rings by acylation and then reduction. So in case of aromatic ring, if you want alkylation or even acylation, this Clemmensen reduction is very much useful for introducing an alkene group into an aromatic compound. Suppose this is this aromatic compound, and you add, so this is the acylating agent, then you get C double bond OR, and then if you do it Clemmensen reduction, ZnHc by HCl, you get CH2R. Okay, so if you want to insert a straight chain alkyl group into an aromatic compound, you first acylate it and then do Clemmensen reduction. It's a very common method of preparation of straight chain alkaline compounds being introduced into aromatic compounds. That was Clemmensen. Now we go to Wolff-Kishner, which takes place in basic medium, unlike Clemmensen's, which was taking place in acidic medium. So as soon as you note this point, it should strike you that base sensitive compounds are not suitable in this particular method. So next reaction, Wolff-Kishner reaction, or let's tell it reduction. Wolff-Kishner reduction. So this is just the opposite of Clemmensen reduction, not opposite but contradictory. So what happens in this reaction? This reaction does not fare with acid sensitive compounds and high molecular weight compounds. So what happens briefly? So you have a carbonyl group. It is converted to methylene group by heating with hydrazone, semicarbazone or azyme. So basically a carbonyl group, it's converted into a methylene group by heating with hydrazone, semicarbazone or azyme, AZINE. What's hydrazone? See, this is a carbonyl group. You treated hydrazine. Okay. Remove this water molecule. What do you get? C double bond. So N NH2. Okay. So this is your hydrazone. So hydrazone is obtained from hydrazine. The NH2 is hydrazine. Hydrazine obtained from hydrazine. Okay. And so if you have semicarbazone, semicarbazone is obtained from semicarbazyme, and hydrazone, if you treat it with another group, then it forms NH. It forms N. Right. So this water molecule gets removed and you form this kind of compound. This is your azyme, and semicarbazyme is NH2, NH, CO, NH2. What is it? NH2CO, NH2 is urea. So from urea you add one more NH2. So this is your semicarbazyme. So from semicarbazyme you treat it with any carbonyl compound, removal of water molecule, then you get C double bond N, NH, C double bond O, NH2. This is your semicarbazone. Semicarbazone. Right? So you have R, C double bond O, R, you treated hydrazine. What do you find? You find C double bond O, N, NH2, R, and then you treat it with C2H5, ONA, presence of glycol, ethylene glycol, and heat it, then you will get R, CH2, R plus N2. So this is basically a Wolff-Kishner reaction. Okay, we'll go into the mechanism briefly. So, conversion of a carbonyl group into a methylene group, that is an alkane, in the presence of hydrazone, semicarbazone or azyme, that is by heating with that, in the presence of strong bases like C2H5ONA, that is sodium ethoxide, and ethylene glycol with sufficient amount of heat gives rise to your alkane via Wolff-Kishner reaction. So let me go to the mechanism. You have R2. This is a hydrazone. Okay. What happens? So you have the base, right? So that is C2H5O minus. So let me tell as base. Whichever is convenient here, since we are using C2H5O minus, basically you have to use very strong base. So this picks up this hydrogen atom. Okay? So this picks up H plus. Therefore you get a minus charge. And you get a minus charge. This tries to form a double bond with nitrogen. This lone pair of electrons goes to carbon, and you have basically its resonance structure with C minus and double bond NH. This is the portion which reacts in this Ulf-Kirchner reaction, this resonance structure, and you add water to it. So what do you have? This being negative, H gets added here, and then N double bond NH. Again you have R2CH, N double bond N minus, because we are in the basic medium. Compared to this hydrogen more acidic, so base picks up the most acidic hydrogen, that is the hydrogen on the nitrogen atom with the double bond with it. So this is picked up, N gets minus charge, then this nitrogen tries to form a triple bond, and then this pair gets shifted here. So what you get is R2CH minus plus nitrogen. Okay, and again if you treat it with water, this picks a positive charge, this picks a positive charge H plus ion, that's a proton, and then you get an alkane plus nitrogen gas is released. This is basically the reaction. So first, formation of an anion of hydrazone, which is then protonated by the carbonyl carbon to form a substituted diamine. And then simultaneous loss of nitrogen and formation of the hydrocarbon. So here in this stage, it's the simultaneous loss of nitrogen and formation of the hydrocarbon. Here in this particular thing, your formation of the anion of hydrogen is the anion of hydrazone, which is then protonated at the carbonyl carbon. So this was the carbonyl compound, carbon of the original carbonyl group. So original carbonyl group you treat with hydrogen or semicarbazide or azine. So you get this. Now this is the hydrazone. Hydrogen gets so it's formation of the ion. Then this is protonated. This is protonated at the carbonyl compound. So remember, suppose if I have a C14 here, so protonation takes place at the carbonyl compound, right? In this reaction, C double bond C, that is the olefinic group, and C double bond O, that is the carbonyl group of alpha beta unsaturated compound, are also reduced, just like your Clemmensen reduction and reduction by H2 by PD or PT or nickel. So catalytic reduction by hydrogen, Ulf-Kirchner reduction and Clemmensen reduction will reduce your both olefinic group and the C double bond O group, that is the carbonyl group, in the case of alpha beta unsaturated compounds. So that were two main reactions of reduction. Some other typical reaction. This is coupling. If you use Na in the presence of ethyl alcohol and then treat it with water in the second step, so this gets coupled to form a diol, vicinal diol. Okay. Then pinnacle reduction. Remember, this is not pinnacle-pinnacle-N, this is pinnacle reduction. In this process, you have a ketone you have a ketone, and if you treat in the presence of magnesium amalgam, in the presence of benzene as a sorbent, or you treat magnesium amalgam in the presence of EiCl4, then if you take magnesium amalgam and treat it, then you'll get this kind of intermediate CCH3, CCH3. Okay, basically this is again a coupling, and then this is how your magnesium gets attached. This, if you treat it with water, then you'll get CH3, C, CH3, OH, C, OH, CH3, OH, plus you'll get MgOH twice. Now, instead of MgHg and benzene, if you treat MgHg, so basically you will get the cis-diol in this form. If you treat with MgHg in the presence of TiCl4, let's for example take this compound. If you treat with this, then you will get that trans-diol. That is OH here, OH here, so this is the trans-diol. Okay, this is again another specific reaction. Okay, point to be noted. Next is addition of secondary amines. I am not going to much detail. So here, aldehyde or ketone with at least one alpha hydrogen produces an enamine. So what's an enamine? Let's take an example. CH, C double bond O, R prime plus, if you treat with a secondary amine, this is your secondary amine, 2 R groups, H plus, reversible, R, CH, C, OH, R prime, N, R double prime, again reversible, okay, this goes here with removal of water molecule. CH. So this is given by aldehyde or ketone with at least one alpha hydrogen atom, double bond, N, R double prime with positive charge because nitrogen forming 4 bonds. And then what happens? R, CH, R, C, this pair basically shifts here, and then these H-boats come here, since this H comes here, this H goes, so this gets negative charge and then double bond is formed. So this is an enamine. Okay. Let me write an enamine again. I hope it's clear, visible. R, C double bond C, N, R dash, and R double dash, this is R dash. For distinguishing purpose. Okay, so this is an enamine. So you will get an enamine as the product. The most commonly secondary amines that are used for enamine preparation are piperidine, basically this is secondary amine, it should have this lone pair which is initiating the reaction. So this is piperidine, then this piperidine, then you have morpholine, this is morpholine, and then you have pyrrolidine. This is pyrrolidine, and this is morpholine. Okay. Now this enamides give rise to many other interesting reactions, which you are not going to study because it's beyond the scope of our syllabus. Let me again tell you a little bit about formation of imines. Remember, some ammonia derivatives like hydroxylamine, they react with your carbonyl group in weak acidic medium to form C double bond N with elimination of water molecule. Now, these derivatives are basically a crystalline solids. So, being crystalline solid, this is a test for aldehydes and ketones. This goes by addition, elimination mechanism. So what's addition, elimination mechanism?
वो अभी निकल ही रहा था क्या?
अमित का है?
नहीं आया अभी तक?
नहीं?
पता नहीं उधर से भी कहीं गया बाहर।
ठीक है। So this is C double bond O. This is NH2G. Where G is anything. It adds when it adds. So this is addition. NHG. This is addition. Then water molecule. And then removal of water molecule to get Ng, where G is anything, OH, any derivative. So this is addition and this is elimination. Therefore the mechanism is called addition-elimination mechanism. Let me look into some examples. R C double bond OR or R C double bond OH, aldehyde or ketone. First, NH2OH, this is your hydroxylamine. In acidic medium, heat, you will get R. I am mainly drawing for ketone. You can draw for aldehyde later. So this is your oxime. Ketoxime or aldoxime. Okay. Next you have hydrazine, N2H4. This is hydrazine. In presence of acid, in presence of heat. This is what you already know. This is your hydrazone. Then NH2, NHCO, NH2, semicarbazide. This is semicarbazone. NH2, NH, this is phenyl group, this is phenylhydrazine. Heat and you will get a brown colored phenyl hydrazone. Okay, and the last reaction is very important, so I'm preferably erasing this so that I can write it better. So this is test with Brady's reagent. That is 2,4-DNP. What is 2,4-DNP? Okay, so this is basically NH2. NH2 is hydrazine. So if you see this 3, 4, 5, 6, so this is 2,4 dinitrophenylhydrazine. So 2,4 DNP is 2,4 DNP is 2,4 2 and 4 dinitrophenylhydrazine. Okay. You treated this, what you will get is nothing but your 2,4 dinitrophenylhydrazone. That's very simple, but why I am telling is that this is a specific test for aldehydes and ketones because of the formation of a red or brown PPT. Or generally it stays in solution, but in bulkier case it precipitates. So this is 2,4 dinitrophenylhydrazone. Okay. So now you should know that these imines are crystalline compounds, which I have already mentioned, and on hydrolysis, so if you again hydrolyze it, imines on hydrolysis will give back its carbonyl derivative from where it comes. So imines on hydrolysis will give back its carbonyl derivative which is used in the preparation of that particular imine. Okay. So in presence of water and heat you will get back this. Now some important things. This imine is also called a Schiff's base, and when Schiff's reagent is added, so when Schiff's reagent is added to an aldehyde or ketone, you get a Schiff's base. So Schiff's reagent added to an aldehyde or ketone, you get a Schiff's base. Schiff's base is basically pink color. Pink color Schiff's base is decolorized by sulfur dioxide, and the solution is obtained by passing sulfur dioxide into Schiff's base is called Schiff's reagent. So pink color Schiff's base, when it is subjected to sulfur dioxide or sulfur dioxide is passed into the solution of Schiff's base, you get a colorless Schiff's reagent. So Schiff's reagent is a test for aldehydes, whereas ketones do not give. Okay? Schiff's base is a specific imine, and it gives only change of color in presence of aldehydes and not for ketone. So reaction with shifts base is given only by aldehydes. It gives pink color with shifts reagent. Okay, so shifts base which is pink in color if it is treated with sulfur dioxide, and if it becomes colorless then it's aldehyde. If no change in color then it's a ketone. Imine can tautomerize to form enamine. The next important set of reactions is addition of water and addition of alcohols to form hemiacetals, hemiketals, acetals and ketones. So that's more important. So let's look into that.